actually work any of them. Before I start any of them, I want to know what's your game plan on each one and why. So, everyone watch. Number one, what's the best game plan? Use substitution. How did you pick that out and know that that was a good plan? The derivative of tangent is secant squared. So I can see that derivative pop out of the other piece. That's easy use substitution. This one. Good. The part. Use substitution doesn't work because the derivative of natural log of y is 1 over not y, not y, right? If this were 1 over y over here, then that maybe just a straight use substitution. But since multiplication and use substitution doesn't work, then we're going to go with our other multiplication option, and that's parts. What about this one? Probably partial fractions. Unless something weird happens with it, that looks good to me, right? Use substitution. Why do I not need partial fractions? Now, don't get me wrong, it doesn't mean partial fractions wouldn't work. But why is partial fractions unnecessary? The derivative of x squared is 2x, and so we cancel that numerator, and I could just use a substitution. Tan inverse. Good. Partial fractions can work because it's a factor, so I hope there's some other way to do it, and it just happens to be tan inverse. We'll be talking about those a little more today. Divide. Just divide, right? Just divide and then do a power rule. No use substitution, no nothing complicated. Just division. Good job. Okay, so let's try them. Any questions so far? Okay, the secant squared canceled. Does everyone agree? And so I'm left with the integral of u to the 1/2 du. Any questions about how I got u to the 1/2 du? Okay, and u to the 1/2, u to the 3/2 times 2/3 plus c, which is 2/3 times tangent to the 3/2 plus c. Any questions about that one? So far, so good? I felt like we could use an integration review, and that's kind of what today is. We're going to learn a few little additions today, but mainly we're just doing more integration. Okay, y, natural log of y, parts. So what would you call dv? Y. Oh yes, dv is y, and u is natural log of y. Sorry, I wrote it. Du would be 1 over y. And v would be 1/2 y squared. And so that integral is v times u, which is 1/2 y squared, natural log of y, minus the integral of v du, which is 1/2 y. I'm going to put the 1/2 in front. Why is it y and not y squared or something? What happened to the y squared? Good. Y squared times the 1 over y, and that's where this comes from. So the antiderivative of that, 1/4 y squared plus c. Any questions about that one? I'll do that in a minute. Okay, this one. Use substitution, what would u be?
X squared minus 4.
Du.
2x.
So you get 1 over 2x du equals dx. And so I can rewrite that integral, the 2x's cancel. It's just 1 over 2. Does everyone agree?
Yes.
So I get natural log the absolute value of u, which is x squared minus 4. If you had done this with partial fractions, don't get me wrong, you could use partial fractions. But if you had done this with partial fractions, you would have gotten, I'm guessing, 1 over x plus 2 and 1 over x minus 2. And so then those can combine into one logarithm by multiplication, and that's why it just works out that you can do this just all together, maybe substitution. Any questions about that? 1 over x squared plus 1 easiest problem on the page if you know the rule. What is that rule? We will memorize those rules on the anyway, I'm going to end up leaving the derivative rules for those off, but I reasoned in my head that was okay because I feel like if you know the integral rules, you know the derivative rules, because they are. You can memorize them. Okay, this one, divide first, and I get 1/2 x minus 3 plus x to the negative 1. Questions about that so far? You also could use long division. You would get the same thing if you were to pretend it was a partial fraction. If you did long division, you'd end up here. So you could wait, but this is faster. X squared minus 3x plus what? Natural log. Why natural log? X to the negative 1 power. Remember, that's the only power that's not a power rule.
Would it not be 1/4 x squared?
It would. Thank you. Any questions about that one? And then a partial fraction. The numerator is already smaller than the denominator. The denominator factors to be x plus 3 times x minus 2. So I have a over x plus 3 plus b over x minus 2 equals x plus 16 over x plus x minus 6. Did I know?
Yeah, the same one.
Any questions so far?
Take this with me.
And you're welcome to stay. Next hour I have that. I have apologized for some getting a free test. So next hour I have a Okay. Any questions so far? A times x minus 2 plus b times x plus 3 equals 2x plus 16. Plug in negative 3 for x and plug in 2 for x in either order, whichever way you want to do it. So if I plug in 2, I get 5b equals 20. So b is 4. Am I going too fast? Is that okay? And if I plug in negative 3, I get negative 5 times a, negative 10. A is negative 2. I'll check if my work. That's always safe to check my work. I'm not messed up. Negative 2 over x plus 3 plus 4 over x minus 2. That is my new integral. So I have negative 2 natural log the absolute value of x plus 3 plus 4 natural log the absolute value of x minus 2 plus c. Just a mental note, I kind of feel like you've all figured this out by now based on the multiple choice, but just a mental note. I did want to combine these two logarithms. How would I go about that? coefficients to be exponents first. So how the calculator might answer this, or how a multiple choice might answer this, they would write the x plus 3 as cubed. Now, you may notice, squared, sorry. You may notice they may lose the absolute values on that particular one. A textbook may, why could you get away with losing the absolute values? Because you're squaring it. So if you noticed an absolute value missing, it's probably for a reason, something like that. And then same thing on this, we could lose the absolute values because it's a fourth power. And then combining those, now you could have made one of those a negative exponent, but I would guess a calculator answer would look like this. Scroll up. I rewrote it like this. One thing I would be careful about, and you might want to check through your homework if we end up not having time to grade. What if there's a number in front here or here? If there's a number in front here or here? Slightly harder. Yeah, something's going to divide out, right? So kind of think use substitution even if you don't write it down. But if there's a 2 in front of the x here, then wouldn't you have a 1/2 come out of the logarithm because of the chain rule? Right, undoing the chain rule because it's times 2. So be careful about that. If you have one of those in your homework, you need to pull that out. You probably noticed that if y'all were checking your homework in the calculator, you probably went, where'd they get the 2 here? Or where'd they get this here? That's where you would go. Oh yeah. Use substitute, that pesky use substitution. Okay. I've never actually said this, so it's time to say it. We're going to memorize the inverse trig, derivative, and integral rules. This is the complex format of them. The one, I don't know, is this +1 on your calculus helper, or does it have a 1? Which the integral rules are not on that calculus helper, they're on the new one. It has a 1. It has a 1. So this is the complex form of if there's not a 1 there. Yes. Well, and I think it's on your new calculus helper. See which one's on your new one. You know the new one? This one? No, new one. You have it. That thing right there. It's an important thing. Just a bunch of animals together. No more new hard rules except inverse. Okay, so they even have secant, cosecant, cotangent. I'm not going to make you memorize those, but I would be aware that they exist and that they're there. It probably wouldn't be a bad idea to memorize them, but they're not going to be on the gateway. Sine, cosine, and tangent inverse will be on the gateway. Okay, any questions about those? You can see that list for all of the integration rules that you might need to be aware of. Now, they put some on there that you might not memorize, like tangent. You could use a U substitution to find tangents inside derivative, right? Or you could memorize it. You've got options at this point. So you can see those on your new calculus helper. Alright, so how would you find this one? Which one does this fall in? Tan inverse. So let's go back and look. Tan inverse is U squared plus A squared. The 1 is on top, so I'm going to go over here and move that 3 out of the way. Right? Because in a rule, there's not a 3 there, but that's not a big deal. We know So 3 times, what is A, by the way? 3. How'd you get 3? It's the square root of that number that's there. So tan inverse of x over 3 plus c. Any questions about that one? So just follow the rule on those. And the 3 and the 1/3 do cancel, so you just get tan inverse x over 3. Now, if you actually undid this integral, it wouldn't look at first glance like 1 over x squared plus 9. You would get the x over 3 parentheses squared. Do you know what I mean by that? That would go where the x was. So this formula kind of simplifies the antiderivative for you so that you don't have to think so hard about that division happening. Okay, this one was on your homework last night and I had you skip it. So I'm answering it for you. This is a topic that is no longer covered in BC, but you will spend a little bit of time on it in Cal 2 if you are to take a Cal 2 class. It is called trig substitution. I almost didn't teach it at all. And last week, Trent Wilson came by and he said, he was talking about Cal 2 and all the things he'd done. He said, I had the hardest time with trig substitution. And I thought, well, maybe I need to mention it at least. Again, it's not in the BC curriculum. You wouldn't have to do a trig substitution, to my knowledge, on the BC exam, but it is something you are skipping if you skip Cal 2. So those of you who are engineering majors will at least need to know that it exists and could look it up in a textbook and what it is. It is tough in that you have to remember trig. It's really clever ways of using trig identities to simplify a problem. If you looked at this problem, which you probably did on your homework before I was like, oh yeah, don't do that yet. What did you try to do and didn't work? What happened? Partial fraction doesn't work because you have the cube root, right? Or the square root, sorry.
Split it all apart at the bottom where I took part of it out.
Just didn't get anywhere, did you? A clever, very clever u substitution makes this a doable problem. And that very, very clever u substitution is letting u be 4 or 2 sine of x. And you could pick most 4 sines. So we're going to try. 2 sine. Let x, sorry, be 2 sine of u. So what I'm going to do is I'm going to change the x to a u, but this time a little different than I've ever done it before. And like I said, sine or cosine work, and you'll see that as we work it. Actually, I'm going to change. I'm going to do cosine. Either one would work. What you have to know is that there's a lot going on in my head to make that choice. That's the hard part of trig substitution. And you'll see it as I do it, but it does take a lot of practice to get to where you see it before you start. Again, not covered in BC, not something you'll have to do on AP exam, but I just want you to know that it exists. So, if I let x be 2 cosine of u, then dx would be what? Negative 2 sine of u d. Any questions about that so far? Thinking. Yeah, I like mine better. They both work. Good. do cosine of u du? Again, at this point, you're probably still like, why in the world did you do that, right?
How can you just say that x is equal to 2 sine of u?
I'm just doing a variable change like you do with any u substitution. So if you, as long as you change your du as well, or your dx into a du, you've just performed essentially a fancy u substitution, except what I'm calling a trig substitution. Yeah. Whatever you want. Now again, at this point, you're probably still going, why would you want to do that, right? I am going to go ahead and change my limits. You need practice with this. I have noticed for some reason y'all don't do this well. You think the limits are still 0 to 1. If I change my x's to be 2 sine u, right? Then what are my endpoints instead of from 0 to 1? Sine of 0 is 0, so I agree it's 0 to something. 0 to what? It was 1 up there, by the way. What is sine of u? Or sine of 1? Oh, wait. No, other x's, sorry. So x is 0. Sorry. So I need u. Sine of 0 is 0, so that's still 0. Yeah, because sine is 0 at 0. But the other one, when is sine of u equal, what are we even equaling? 1/2. When is sine equal to 1/2? 5 or 6. So our u's would change, our endpoints would change, because our x's changed to sine of u's. First and fourth. Okay, so those were originally x's, but I've changed every variable to u's. So those need to become u's inside the change.
First and fourth is sine, first
Second,
and
first and fourth. That one doesn't come up here. Square the sines 2 sine of u. Now you could always go back, but I would rather just leave these endpoints to change. Square the 2 sine of u. Has anyone any idea why this trig substitution is going to help me at all at this point?
equals 2 minus 2 sine 2 plus 2 sine.
Why is that nice? Why?
Because 1 minus sine squared u is cosine.
And is it nice to have one single function under that cube root or that square root? So it's a fancy trig substitution to allow you to use a trig identity. Now again, you have to think about how much went on in my head to make that happen. Because I had to go, okay, what's going to give me cosine on the inside that I can use? So it was tough. Now again, I could have picked cosine there. I would end up with a cosecant at the end, which is fine too. I like secant squared better, which is where we're going to end because the antiderivative is tangent, and that's a little smoother, but you could use either one. So, simplifying some more. These are multiplied together, agreed? The 4 and the sine of u, or the cosine of u. Like I said, this is not in BC, but those of you going on in math, this is something they do in Cal 2. They spend a little more time on it than we're going to, because as much as I want to expose you to it, I don't want to spend your valuable time doing something that's not on the BC. stop at that. The negative 3/2 power, I can raise 4 to the negative 3/2 power. Does everyone agree with that? I can do that. It's the square root of 4, which is 2. 2 cubed is 8. It's 1/8. Does everyone know why? You need to know that part. Does everyone know why 4 to the negative 3/2 power is 1/8? Do you? You need to know that. That comes up in regular usage. So we have 1/8, and I'm going to go ahead and move the 2 out as well. And then I have this cosine squared to the negative 3/2 power, right? Well, the 2's, what happens to the square root of square? They cancel, so I get 1 over cosine cubed on the bottom times cosine of u. And what is cosine of u divided by cosine cubed of u? 1 over cosine squared, or secant squared. Why would I call it secant squared? Because that's one of our rules. Tangent is the antiderivative of secant squared. So you can see how much has to go on in your head to do this. 1, would you ever be able to do this without knowing your integration rules? Because I had to kind of anticipate a secant squared coming. 2, would you ever be able to do this without knowing your trig identities? No. So those of you going on in math, you can kind of keep in mind that to get to the place where you can do this, you gotta know those integration rules really, really well, and you gotta know your identities really, really well to be able to think through this process. So this is tough. And so you get 1/4 tangent of u from 0 to pi over 6. Tangent of pi over 6. What is the tangent of pi over 6? Let's get that. Good. Tangent is opposite over adjacent. Everyone agree? 1/4 times 1 over the square root of 3 minus what's tangent of 0? 0. So the answer to this, he said square root of 3 over 3, right? So it's square root of 3 over 12 is the final answer. Look at your homework that this is on. Is that an answer? Any questions about that? So again, you're not going to have homework over this. I just wanted you to be expecting. Where are you going? No. Okay, this is your homework. We also have one question we need to do together on last night's homework, and then I'll let you pass it. It is number 13. Number 13 is tricky also. Again, I don't think I'll show up on the BC exam, but hey, I can say I showed you how to do it. Number 13. Why is 13 hard?
Because you can't use this.
Everything cancels out. Yes. Well, we need to do number 13 together. This is mainly the homework is use substitution practice, because based on my observations of you, you need help on use substitution. So what you're going to do, this is mainly use substitution. It's also inverse trig, though. There's use substitution and inverse trig thrown on those, so covers both of those. Do what? 13. Okay, you ready? 13. Is everyone okay if I skip to the already defined spreadsheet that helps me find those multiple choice and deployments so that y'all get to see what they look like in each topic. And sometimes I need to check them closer. But I did, after Trent came in, I did decide I wanted to check Trent anyway, so it worked out. Okay. Any questions so far? If you have a denominator with a repeating linear factor, the way you set that up using partial fractions is you make your second piece have the denominator of x minus 2 squared already. Why is that helpful? Then they will both have an x minus 2 with them when I multiply by x minus 2. So the only time you do this is if you have a repeating linear factor in the denominator. So an x minus something squared. Or just an x squared. So that one needs an x minus 2 on top and bottom to have a common denominator. And then we can use the Heaviside method still for A, or for B. We actually cannot use it for A, but I'll show you how to find A. For B, though, I can plug in 2 into every x. And so I get B equals 2, right? 24 minus 22. You can. Yes, you can do that. Okay, everyone agree that B is 2. So now I can't go do Heaviside on to find A because there's nothing I can plug in to get the B to cancel, right? So now it becomes a system of equations type thing. There are a couple of ways you can do it. I still like pretending I'm doing the Heaviside method. I can't get the B to cancel, but since it's just 2 anyway, you could still plug in anything you wanted in for x. Like 3. 0 would work too. I like 3 better. Okay, that makes sense. You can do that too. I don't know. I like 3 because then it says just 1 over here. But you can do whatever you want. The 0 works good too. Anyway, pick any number you feel like picking. You can pick 100 if you want. I wouldn't. Because then you have to multiply 100 by 12. You can do it. But I would probably pick something like 3. Because you get A times 1 plus 2 equals 36 minus 22, which is 14. Subtract the 2 over and I get A equals 12. Any questions about that so far? Good so far? And so now you can set up your integral. It is slightly different than the other partial fraction integrals. So I have A over x minus 2. But then I have B. What was B over? So the antiderivative on that is slightly different. Oh, we lost a 3. So wasn't there a 3 in front? The antiderivative of 3 is 3x. The antiderivative of the second one is 12. Natural log of the absolute value of x minus 2. What in the world is the antiderivative of that? How do you do it? So pretend this was on your over here. but we'll do it. du would be 1 dx. And so I get the integral of 2 over u du. 2 over u squared du. And you see why it's not a logarithm, right? Because it's u squared instead of just u. And what would you call that instead of u squared, 1 over u squared? You'd have been -2. And you'd add 1 to the power and divide by that new power. If you add 1 to -2, what do you get? -1. So you get 2